Okay, so in this video, we're gonna talk about how do we use the data to get these tree structures. Specifically, we're gonna introduce the greedy top-down algorithm. This is for classification. Okay, this algorithm is more or less obvious and has been rediscovered in literature many times. It's naturally recursive. Uh, if you took any data structure course, uh, recursive means you can write your functions using some recursive patterns with some recursive patterns. Okay, so now let's see how do we find this greedy top-down recursive algorithm. Okay, so let S to denote the let S be a subset. So this means subset. Let S be a subset of the 1 to n, the index set. For example, we have at the beginning our data point is x1, xn. So S means maybe some of the class, some of the central point we give the index, we collect their index. We give the index set S. Okay, and at the beginning when we initial this algorithm, the top level of this algorithm, this S is just all the data sets. Okay, and how do we, so we start from the beginning, we have all the sample points, and we grow the tree. I will give you the pseudo algorithms, pseudo code for this algorithm. So we grow the tree S. Okay, in which case we grow the tree if all the points in this node have same label. So we can write down in this way. So if all the points yi equal to this same label C for all I belongs to this index set for some class C. Okay, then return the new leaf. In other words, if all the nodes in this region has the same node, same labels, we return the leaf with label C. Okay, and else okay, maybe we should have the curly brackets here, and else we keep going, right? We choose the best splitting, else we choose best splitting feature. I think for our course, you do not need to implement this algorithm from the scratch. I think almost all the machine learning package with regression trees already implement this for you. Here you just know the basic ideas. Choose the best splitting feature. feature j, and the splitting value. For example, in our previous first example, why do we choose x2 as our top node? Okay, so first we need to choose the node. Also at this branch, why do we choose x3, not choose x1 or x2 again? Okay, so we need to choose the node splitting features, and we also need to decide what's the best way to splitting rule. Best splitting rule. Splitting value. Okay, splitting value beta, we call it beta. And we'll come back to this. More details later. Okay, once we find the best splitting feature and the splitting value beta, we can define our sub nodes. One we call it as left node, which is equals to all the index from our parent node. All the index from parent node. If the splitting condition, splitting feature splitting feature remember, in our feature space, I denotes the S sample point, J to denote the J's feature. So if Xij is less than beta, we go to the left. If S, otherwise we go to the right. Okay, and then return the new node. So in this new node, we need to return the splitting node, splitting feature. We need to return the splitting value, decision value beta, and then we grow the further trees. We grow the left tree, or we grow the right tree. Okay, so this will be our complete greedy top-down algorithm. Okay, and now for this is the key steps, right? How do we choose the best splitting feature J and the splitting value beta? Okay, how do we find, how to choose best split? So this algorithm is done, but here we give a little bit more details on how to choose best splittings. So how do we choose the best split? So among all possible split, okay, for example, if we have the categorical features for the x2, the weather, we can have 3 splits, right? And for the x3, although this is quantitative variable, but when you have the few observations, for example, if our data only has, I'll give more details how to cut this quantitative decision boundary. So once we know what's all the possible is not infinite, it's a finite possible ways to split. Okay, and for each set S. Okay, we're gonna define what's the cost. We need to determine what's the cost of this split J, of this S, of S. Okay, and then choose the split that minimize the cost. On the left node and the right node. Or it's more commonly, you can use this summation of the cost, but also a lot of cases you want this cost to proportional to your sample size, because if you want to, you do not want the few points that influence too much, so you want the point that influence that proportional to the sample size. So additionally, we can also using the weighted average. So which is SL plus S right SL JSL plus SR JSR. Okay, so this weighted loss. And this means the sample size, or you can say it's a cardinality. Cardinality of S. So in other words, number of elements in S. So the question is, how do we define the cost for each split? So what's the cost on split? So think for a minute, how do we define a cost for a split? Maybe the first trivial method is, you can think maybe we can just use the GS, so method 1. But this will be a bad method. Okay, maybe we can just define the GS to be the number of the points not in this class C. Okay. So here maybe one example. Suppose our at the initial level we have 30 data points, and among those 30 data points we have the 20 points we labeled as C. Okay. And we have the 10 points labeled as not C. Maybe we only have 2 labels, label C and label D. And suppose we have this split. Okay, suppose our first splitting rule give us the left node and the right node. Okay, suppose in this further splitting we have the 10 points is labeled C, 10 points labeled as D. On the right node So this is you can think this is S. This is SL. This is SR. We have the 10 points not labeled C. Okay. So on this hand we have we all labeled as with 10 points we all labeled as C. Okay. So this is one scenario. And we have another scenario. Okay, we have same starting point. We have 20 points labeled with C, 10 points labeled with D. Okay, so we further split, we find the feature, and we further split. We get two nodes, SL, SR. Okay, and in this case we have the 10C, 5D. Okay, again here we have 10C, we have 5D. Which tree do you think is better split? Which one is better? So I will let you pause and think for a minute. Actually, for the splitting on the left tree, at the beginning stage, we have what's the chance you to be classified to find the right label? So you had 20 over 30, right? 2/3 chance, and if we go to the right node, we have 100% to find the correct label. But on the other hand, on the right hand side, we have the 20 over 30 at the beginning. And we have the 10 over 15. 10 over 15 it's 2 over 3, right? So, and same thing here, 2 over 3. So actually, the splitting on the right hand side didn't do anything. This splitting didn't increase. You didn't get any further information based on this split. So now let's talk about what's the cost. If we use this as a cost function, the cost at the beginning node will equals to how many of them are not in the class C, right? So 10 of them not in class C, so it's 10. So this SL is also equal to 10. Okay, same penalization, and GSR equals to 0. Okay, we have the lower cost because this classify all the points. So this node has a pure node, which means all the points are in the same class. On the other hand, this cost is 5. This cost is 5, and this cost is 10. Okay, and if we summation this together, so we add this together, we get 10. We get this together, we also get a 10. But actually, the left tree will have better performance because on the right node, it gives 100% accuracy on the prediction. If we use the weighted average means weighted average, we have the 20 points here and 10 points here. We have 30 points, and we have 10 plus 0. Okay, and this is the weighted cost. Equals to this, so it's 10 over 30. And on the other hand, on the right hand, the weighted cost is equals to 30 wait, sorry. So we should also multiply the cardinalities on each split. So 15 multiply 5, right? Plus 15 multiply 5. So this equals to, the cost equals to, so 15 cancel 15 is 2. So it's 5, right? Cost is on the, I need to rewrite this part. This equals to, so sample size 10, sample size 20 multiply 10 plus 10 multiply cost is 0. So the left hand side of the cost is 20 over 3. So which will be much larger than the split on the right, which is counterintuitive, right? So which means this is the bad cost. This is the bad cost. Okay. So this is just one example to show you how to come up with some cost. Actually, the most popular way to define this cost is to using the entropy cost method 2. Called entropy cost. Okay, this is used in many algorithms. This entropy, the idea is from the information theory. Okay, so let's see how do we define this entropy theory, entropy cost. Let y be a random class variable. And we have the probability if this you random pick a case, the label is C, has a probability we denote as PC. Okay, so the price, okay, the surprise of y is class C is to be defined by the negative natural log base 2 PC. For example, if we know if PC equals to 0, okay, PC equal to 0, which means we have very small chance to be classified in class C. Okay, and then if you observe C, you should have very infinite big surprise, right? So PC equal, so negative log 2 0 will give us equal to infinity. So we have, so if the probability to observe C is 0 and you observe the C, so you will have infinite big, so you have huge surprise to C, label C. Okay, and if the probability C equals to 1, okay, so which means almost surely we will flip a coin, we will get a label C. So in other words, this information, let's see, is a log 2 1, which equal to 0. Okay, so it's not a surprise. To CC. Okay, so this label, this quantifies the surprise of y to observe the class C. Actually, in the information theory, this surprise is equals to expected number of the bits information we need to transit happen to be events happen to a recipient. Often this means the using of the bits. So this is, there are some interpretations from information theory. Okay, so this is the expected number of bits of information we need to transmit. Which event happened to a recipient who knows the probability of the event. Okay, if you only knows, if you have a long sequence of the 0 1s, okay, and the recipient knows what's the probability to observe 1. Okay, so if you want to send this a sequence of this information, so this will be the expected number of the bits to be transmitted. Okay, so this is where this come from. And the entropy, and now we are ready to introduce the entropy. The entropy of an index set S is the average price surprise. Which is defined by HS equals to, if you have count how many different labels in your set in your current node. Okay, if we have only two labels, then this is just the summation is over 2 labels. We count PC and times natural log. So it's weighted average of the PC, right? You can think this PC is just the proportions of the points has label C. So proportions with label C. Okay, yeah. So example. Okay, if we have two labels, spam or not spam. Okay, we call it C spam, and not spam we call it D. Let's call it D. Okay, so negative C, negative, not negative C, so negative PC. So first you count how many points in your current node classified as C proportion, and you weighted by the average. Okay, and then minus PD log PD. Okay, so we use this to denote the cost for the splits. Okay, so if all points in S have same label, okay, so what will be the cost? The cost will be so if you have all the nodes with same label, so this which means that you're done with your splitting. This is a good split, right? You have 100% the guess is correct. So this means and you have 100%. So PC is 100%. So it's 1 times log 1, which gives you 0. Low cost, right? If the half split, if half of points, if half of the points in class C, half in class D, okay, then we have the HS equals to negative half times log half minus half log half, which equals to negative half, which will give you 1, actually. Okay. So another extreme case is if all the points in your node S if all points in S have distinct label, so which means you have very bad split, okay, then the HS, because each point you have the 1 over n, right? 1 over n proportion, you times log 1 over n, and you repeat this for each point. So you have the negative, you add n times, so you have negative log 1 over n, so which means you have the log base 2 n, okay? So this will be a big number, so big cost. Okay, so therefore another way to think the cost, this entropy cost, is the measure of purity of a node. Okay, or you can think as similarity. If all your points in your node is same label, you have low cost. If all distinct label, we have high cost. Maybe let me show you another plot for this scenario. So for the plot given below, this shows the entropy of the PC, okay, for two label case. Okay, so if you have the 100% of the labels are all in C, or 100% of the labels are all in class D, you have low cost. The worst case is 0.5. Okay, you have half mixed. You have the highest cost in the middle part.